Hello everyone, my name is Archim and today I'm going to be presenting my operating system for CSCI 92 Principles of Operating Systems. And my operating system is called BuoyantOS because I was named after Archimedes. So on a high level, what's BuoyantOS doing? It's an OS for the NXP Freescale K70 F120M. This board is running a ARM Cortex M4 processor in thumb mode, and the board also has a variety of devices. Some of the ones that we're using are push buttons, touchpads, LEDs, the various UARTs. There's a couple of ADC devices like the potentiometer and thermistor, as well as an SD card slot. But this is not an exhaustive list. So for the user interacts through supervisor calls, and there's 37 of them spanning around 6 flavors. These flavors are memory management, device independent I/O, interacting with the file system, various timers, multi-programming, and facilities for semaphores. So let's go into more detail about each of these. So for memory management, I chose to write an AVL tree based allocator using the first fit algorithm specifically. First fit doesn't really make sense at first for an AVL tree, but it's basically just means we're going to try and find a free block as fast as possible. And that just means we're going to go into the subtree, which is least height. And this is very efficient compared to a linked list. In terms of big O, the AVL tree is going to be log n, whereas the linked list is linear. But the AVL tree has an extra factor t, which is how long it takes to implement. And t is much higher for the AVL tree. Another reason that I did like the AVL tree was that it kind of efficiently treated any size of block. So like a lot of the alternative allocators, for example, a buddy allocator, they round up to a size of 2. I know that's not all of them, but that just seems kind of wasteful. And like at first look, that's why I kind of like the AVL. And on the right here, you can see this actual supervisor calls for interacting with the memory management system of BuoyantOS. You have the classic malloc free and some other commands. And then here is what a memory header looks like. Unfortunately, it doesn't fit in one double word. It's 2, but I felt that it was worth it. So let's actually see what the allocator looks like. So this is the operating system. And first we can just look at the memory map. And this is after the OS has done some of its basic allocations. So we see a bunch of blocks. We can see whether or not they're allocated or freed. We can see where the block starts and ends. And then we can also see its PID. 0 is the OS and 1 is the shell process. And then we can also look at the tree format. So this is basically showing the AVL tree. Now we can see the same information, but we can also see the location of the header, the height of the subtree, the maximum free within that subtree, the left and right headers. Okay, so kind of the next flavor of supervisor calls are those relating to device independent I/O. And this represents a common interface for all devices that the user can use to interact with them. And besides making it just very simple to add new devices, it also allows things like pipes and redirection. And it also, within user programs, it can be convenient for a helper function, say, to not know which device it's interacting with. And on the right, you can see the actual supervisor calls. So get and putc, puts, opening and closing, deleting, and creating. Okay, so for the file system, BuoyantOS has a FAT32 driver that works via the K70's SD card slot. And I do support nested directories. Another important point is that all reading and writing within the driver is done in the form of blocks or clusters. So we have a cache. And the cache has room for at most 8 blocks at a time, although this is pretty easy to change. And all reads and writes are abstracted to fetch into the cache and then read from that cache. Um, you might be asking, like, what happens if the cache entry gets invalidated while we're reading from it? And that's why the every cache entry has a semaphore associated with it. Um, and then in addition, we're going to need to evict cache entries. So when you actually read from the disk, you have to specify whether you're going to be reading or writing. Um, and if you fetch a cache in read mode and then write to it, it's not going to do anything. Um, and this made things much easier to implement. Um, on the user side, a lot of the interaction is also done via the device independent I/O. Um, All right, so the next thing is timers. So BuoyantOS makes use of three timers, and those are the flex timer, which is used for keeping the current date and time in relation to the Unix epoch, as well as the MS-DOS epoch for the purpose of FAT32. Um, there's also a PDB timer that allows users to execute callbacks after a specified number of milliseconds. And this is one-shot mode, so it's just one interrupt. The user's callback gets executed once. So they might have to do some convoluted things to get a repeating callback. And then lastly, we have a sysdig timer that allows the operating system to provide some multi-programming functionality. The user doesn't do anything with the sysdig timer. And again, on the right, you can see some of the syscalls. Okay, so for multi-programming, I chose a quantum of 50 milliseconds. And the way this is going to work is that every 50 milliseconds, the aforementioned sysdig timer is going to fire an interrupt. And then in that interrupt, BuoyantOS is going to go through a circular doubly linked list. And this is just using a simple round robin scheduler. Every process is in either the ready, running, or blocked state, as well as a special kill state. And BuoyantOS is going to skip the blocked processes in that doubly linked list. Although if the last process is blocked, then that process is necessarily a shell and it'll get woken up. The user and the operating system can manipulate the states of various processes. So through syscalls like block, blockpid, yield, wake, etc. And this does mean that a user program could block every other process and then just run for eternity. But it's okay. And then also the users who are maybe writing programs to process data with multiple processes might want to make use of semaphores. So I've implemented semaphores using a fixed length 32 item buffer of blocked PIDs. And so if you try to down the semaphore while its resources are exhausted, then your process will get blocked and the PID will get stored in the buffer. It is possible for, let's say, somewhat 33 downs would acquire the resource and then fill the buffer. The 34th down would then have to busy wait, so just yield in a loop. But hopefully that shouldn't be happening too often. Similar to file streams, semaphores are visible to the user as just identifiers, so just UN32s. And that's so that processes can't just manipulate semaphores or perhaps corrupt them. Obviously, this is kind of a toy operating system, but you don't want the user to be changing the block PIDs and then forcing the OS to wake up some random process, for example. And besides being exposed to the user, they're also used internally. And there are a few critical regions that get locked. So some of them are malloc and free, and that's the reason why the semaphores use a fixed length buffer, because if you want a dynamically allocated buffer, then you need to recursively call malloc and free. There's also the UART. So fputs will lock the UART, and so will fputc. And so then if you can imagine a situation where two processes call fputs without the semaphore, characters might get intermingled. Another thing that gets locked is each PCB has a list of streams, and this gets locked as well. And then finally, it's sort of ironic, the list of user-created semaphores has a semaphore for itself. And one unfortunate thing is that I don't have support for semaphores with more than one acquirer yet, but hopefully I can finish that before Friday. So that's the end of the presentation. Let me just show a video with some of the multi-programming capabilities. It's just going to run this dummy program called Flash LEDs, and that's basically just going to flash the LEDs on and off at different frequencies until switch 2 gets pressed. So let's see that video now. Here you can see that the orange LED is flashing at one frequency and the blue LED is flashing at another. And the blue LED is using the PDB timer and the orange LED is just using a busy wait.